let's practice maximum likelihood by looking at an example using the binomial distribution. So let's assume you're playing basketball, you attempt 6 free throws and 5 of them make it in. And let's also assume that each free throw has an equal chance of getting in and your free throws are also independent. All right, so in other words, we're assuming that we have a random sample of size 6, 5 of them make it in. So in this case then, if we define a random variable x as the number of successes, the number of shots that make it in, then in our case here, we have x equals to 5, and we have 6 attempts, so we have n equals 6. All right, so in other words, our random variable x has this binomial distribution with n equals 6 and p unknown. So p is the probability of the shot making it in the basket. Okay, so p is unknown. This is what we're looking for based on the fact that you have 6 shots, 5 of them made it in. Okay, so our PMF then we know from probability is, here we have n choose x times p to the x times 1 minus p to the n minus x. All right, so then we know that we can take this and we get our likelihood function. So let's write down our likelihood function. So it's just the exact same thing as this joint PMF here. So we have n choose x times p to the x times 1 minus p to the n minus x. So if we're doing maximum likelihood, we need to maximize this likelihood function. But it's a lot easier, like we said before, to take the log and then maximize that, because maximizing the log of a function is going to be the same thing as maximizing the function itself, since log is a monotone transformation. All right, so our log likelihood, we have the log of n choose x plus x log p plus n minus x times log of 1 minus p. All right, so now we have our log likelihood. What we need to do is take our derivative. All right, so this is a constant with respect to p, right? Because we're differentiating with respect to our parameter p. This, no p in it. It's just a constant. When you differentiate, this disappears, goes to 0. All right, so this goes to 0, and then we have x times log of p. We're taking the derivative of this. We know the derivative of log is just 1 over p. So we get x over p for the derivative of this piece. And now we have this final piece. We have n minus x times, again, we have log, so we put 1 minus p in the denominator, and then we take the derivative of this inside piece, 1 minus p, with respect to p, and that's just a minus 1. Okay, so now we have the first derivative of our log likelihood. It is x over p plus n minus x over 1 minus p times negative 1. Okay, so we're looking for the maximizer, so we know that we need to set this equal to 0. So we set that equal to 0. So we have x over p is equal to n minus x over 1 minus p. So now we need to solve for p, right? So do our cross multiplication and solve for p, and we get p hat equals x over n when we finally solve for p. So this is what we call our maximum likelihood estimate, because it is the value of p that maximizes this likelihood function. We maximize the log likelihood, but same thing. All right, so this is our maximum likelihood estimator. So when we have, like, just in its general form where we have x and n like this, we call this our maximum likelihood estimator. And then when we actually plug in what our x is and what our n is, we call that our maximum likelihood estimate. So our maximum likelihood estimate here is 5/6. Okay, so again, The maximum likelihood estimator is this like process and this function that you get at the end. And then the maximum likelihood estimate itself is where we plug in the actual numbers specific to our particular problem. Okay, so again, just to wrap it up, in order to do this maximum likelihood stuff, we first had to write down the PMF or PDF, and then we write down the likelihood. And now we're thinking again in this likelihood as P being the variable and X is constant. We take the log, we take the derivative, set that equal to 0, solve for P, and when we have solved for P, then we get that that value of P is our maximum likelihood estimator. And then we can go ahead and plug in what is X, what is N here, and we get our maximum likelihood estimate. And of course, last step would be to take the second derivative because we do want to check that our likelihood is concave down here rather than concave up, right? Because we're looking for the maximizer, so we need it to be concave down rather than the minimizer, which would be concave up. So take that second derivative and make sure that you actually have a maximum likelihood estimator and not like a minimum likelihood estimator.